To solve this problem, since I'm looking at the forces acting on a box, I'm going to be looking for, starting with a free body diagram. So I'm going to start with a big free body diagram. So here's my dot. This dot represents the actual box itself. And let's think about all the forces that act on the box. First off, there's a rope that's pulling it that supplies tension. So there's our rope right there. And the tension is going to be 30 newtons. So there's my T. The box is sitting on a surface. So anytime that happens, the surface is going to have a reaction force, which we call the normal force. So I'm going to use this Greek symbol eta to represent the normal force. And the normal force is 90 degrees to the surface itself. When I'm looking at this box, the box is going to have weight to it. So it's going to go down. It's going to be the weight. And that's going to be the weight. And I'm actually going to write that as mg. So not just weight, but I'm going to write it as mg. And finally, I'm looking for the coefficient of friction between the box and the floor. Let's see, in this problem itself, it tells me that the box is moving at a constant velocity. So that means if it's moving at a constant velocity, the acceleration is equal to 0. So there is no net force on this box. So as I move it, it's going to be an equal force going this way. I cannot draw very well. And I'm going to use a cursive F to represent friction. So no net force, that means all these things are going to add up to 0. My next step is going to be to sum up the forces in the x and y directions. So I'll start with a sigma, which means summation of the forces in the x direction. So I've got the sigma, which means sum, F tells me what I'm adding up, and x is more specifically which one of these components. So that's going to equal, well, it's either going to equal ma or 0. Since there's no acceleration or no change in speed in the horizontal direction, it's going to equal 0. Then that's going to equal all the forces in one direction minus all the forces in the other direction. So I'm going to pretend I'm a math class and say that all the forces going to the right minus all the forces going to the left. So that makes this kind of easy. Now I'm going to sum up the forces in the other direction. That's going to be the perpendicular direction, or the y direction. Sum of the forces in the y direction equals 0, and that equals all the forces in one direction minus the other forces going the opposite direction. So I'm going to do all the forces going up minus all the forces going down. So I'm going to treat it kind of like math class and just make up the positive and down the negative. So this is great. This gives me two equations to start with. The first one is going to be 0 is equal to T minus friction. The second one is going to be 0 is equal to the normal force minus mg. Now if I look at this and I think about which of these variables I know and don't know, well, what I don't know is I don't know the friction and I don't know the normal force. So I need to get rid of those. To get rid of those, I'm going to use substitution. So the first thing I'm going to substitute for is to get rid of friction is I'm going to substitute using the definition of friction. That is that friction is equal to mu times eta. So I'm going to replace friction with mu times eta. So let's see, let's do a little bit more work here. I know that I know that 0 is equal to tension minus friction. So tension is equal to friction. Therefore, tension is equal to mu times eta. So I don't know if you noticed what I did there. All I did was I took this expression and just rearranged it so I could isolate T. All right, so T is equal to mu times eta. But I have a problem. I don't know what eta is. See, I circled it up here. So I need some way to figure that out. But I do know what mass is. I know what gravity is. So I can use that second equation to describe eta. So I'm not using any kind of generic equation. It's the one that I created in the very beginning. So let's see. That's going to say that eta is equal to mg. All I did was I took the second equation and isolated eta to get that. All right, and then I'm going to replace, wherever I see eta, I'm going to replace it with mg. So up here is the eta, and I'll replace it with mg. T is equal to mu mg. So that's great. In terms of the things I circled in the beginning, I've got these variables. I've got m, I know what t is, and I know what g is. I'm looking for mu. So mu is equal to T divided by mg. So mu is equal to the tension, which is 30 newtons, divided by the mass, which is 10 kilograms, times g, 9.80 meters per second squared. It's not a negative value because we're not going back into kinematics and focusing on the direction of g. We already accounted for that when we drew our fluidity diagram, so I don't need to worry about that part of things. So if I do this, I get mu to be equal to 0.306. The coefficient of friction does not have any units to it, so that is the final answer for the problem.